You might think these towering structures are smokestacks, but what billows from them isn't smoke at all. In fact, they serve a completely different, yet crucial, purpose at power plants, especially nuclear ones that don't combust anything. The real secret lies in managing the immense heat generated, and it's far more ingenious than you might imagine. The largest class of power plants, known as thermal power stations, rely on steam turbines. After the steam passes through these turbines, it must be condensed back into liquid water. It seems counterintuitive. After expending significant resources to heat water into steam, even more energy is needed to cool it back down. An inefficient cooling process could negate much of the electricity generated. So, engineers have devised remarkably creative and efficient methods to cool vast quantities of water, often millions of liters or tens of thousands of cubic meters per hour. Not all cooling towers share the iconic shape we recognize, but there are exceptionally clever reasons behind that design, and I'm going to build a model in the garage to show you exactly how they work. Power plants could simply vent steam into the atmosphere, but this is generally avoided. Firstly, it would be environmentally detrimental. The release of heat, moisture, and noise could negatively impact local wildlife and weather patterns. Secondly, it would lead to a significant waste of water. The feed water used in boilers is often meticulously treated to prevent corrosion and mineral buildup in the machinery, making it too valuable to simply release. Thirdly, this approach would squander a considerable amount of energy. It is generally more economical to cool the steam just enough to condense it back into liquid water for reuse as feed water. But even this presents an enormous challenge. As discussed in a previous video, power plants do consume a considerable amount of energy for their internal processes, including cooling. While the net output is positive, any energy diverted for these operations is energy not delivered to the grid, highlighting the need for highly efficient cooling. One straightforward option is to utilize an existing cooler water source, such as a river, lake, or sea. Many power plants, for example, draw water from a lake, circulate it through condensers, and then release it into a channel where it slowly circulates back to the lake's opposite side. This slow circulation allows the water to cool before returning to the plant. However, not every thermal power plant has access to a suitable lake or river for cooling, and there are environmental impacts from heat discharge and water intakes that require careful consideration. Consequently, many power plants employ cooling towers instead. You are likely familiar with various machines humans have invented for cooling. You might even be enjoying the comfort of such a device right now. However, as mentioned, the simplest way to cool something is to allow natural physical processes to take over, essentially waiting for entropy to do its work. Since the ambient temperature is usually below boiling, heat from steam will naturally transfer to the surrounding air if permitted. This principle forms the basis of how many cooling towers operate, albeit with a clever twist. To demonstrate this process, I designed and built a model cooling tower right here in my garage. Constructed from laser-cut acrylic strips, its carefully chosen shape, once assembled, forms a clear, functional representation of a real tower. This is a model of a natural draft tower. While not the most common type, its simplicity and iconic, recognizable form make it perfect for this demonstration. You may have noticed the holes drilled at the bottom of each acrylic strip. This tower requires a way for air to enter at the base. A close inspection of real-world towers reveals similar openings around their bottom circumference. Steam from the turbines does not directly enter the cooling tower. Instead, there's a separate stream of water, aptly called the cooling water. The steam is condensed into liquid water in a condenser that is cooled by this cooling water, which then flows between the condenser and the tower. I'm simulating this with a bucket of hot water and a beer brewing pump. This hot water is pumped to sprayers inside the tower. Basic thermodynamics teaches us that heat naturally flows from hot to cold, meaning water can only be cooled to the ambient air temperature through simple convection. However, a deeper understanding of thermodynamics reveals a clever trick to significantly enhance this cooling process. The layer of material situated below the sprayers is the key. This material is known as fill. For my model, I'm using a dehumidifier pad, but in real cooling towers, the fill consists of specially designed plastic layers. This fill maximizes the water's surface area by breaking it into tiny droplets or thin sheets as it descends. The objective is to expose as much hot water as possible to the upward flowing air, a technique known as counterflow, which is central to the entire process. While we typically refer to the dry bulb temperature, the one found on weather reports and thermometers, air also possesses a wet bulb temperature. This is measured by passing air over a wet thermometer, causing water to evaporate. The drier the air, the more readily evaporation occurs. This process requires latent heat, which is absorbed from the liquid water, thereby cooling it. Consequently, as long as the ambient air isn't completely saturated, 100% relative humidity, water can be cooled below the dry bulb temperature through evaporation. The lower the air's humidity, the greater the evaporation, and thus the greater the cooling potential. While evaporative cooling is a natural phenomenon, evident in how our bodies sweat to regulate temperature, its application at this industrial scale is truly remarkable. And it's not the only innovation in a natural draft cooling tower. For that, I need to show you a cool graph. This complex-looking psychrometric chart, a subject worthy of an entire college course, helps us understand some crucial physical and thermal properties of air. Firstly, as air temperature rises, its capacity to hold water also increases. Much like hot tea can dissolve more sugar than cold tea, hot air can hold more water than cold air. Secondly, as air temperature increases, its density decreases. Confusingly, the psychrometric chart actually shows specific volume, which is the inverse of air density. So, as you move up in temperature, these lines slope downward. We all know hot air rises. Less intuitively, the same principle applies to humidity. Holding temperature constant, increasing the water content in the air actually decreases its density. This is because water molecules are lighter than the nitrogen or oxygen molecules that make up most of our atmosphere. Consequently, humid air is more buoyant than dry air, a phenomenon that forms the second key principle of a cooling tower, convection. As the hot water transfers its heat to the air warms and becomes buoyant, rising within the tower and drawing in fresh air through the bottom intakes. Simultaneously, some of the hot water evaporates, removing additional heat and making the air even more buoyant. This dual process not only cools the water but also generates a powerful natural draft, continuously pulling in fresh, drier air. Remarkably, apart from the pumps and minor control systems, these towers operate with no moving parts. For just the energy cost of spraying water, an enormous natural convection current is created, drawing vast volumes of air into the base, up through the fill, and out the top, efficiently rejecting massive amounts of heat into the atmosphere. This visible plume, often mistaken for smoke, is actually just water vapor condensing into tiny droplets as the saturated air mixes with cooler ambient air at the top of the stack. Essentially, it's a giant cloud machine, which is why the plume is typically more prominent during colder winter months. I was genuinely surprised by the efficiency of my small model tower. Pumping water at approximately 50 degrees Celsius, I observed the outlet temperature dropping by about 17 degrees Celsius, a transformation from a perfect cup of coffee to a lukewarm shower. The sheer volume and warmth of the air exiting the top were astonishing, defying my initial assumptions that these processes might not scale effectively due to turbulence. It proved both highly effective at cooling the water and visually impressive on camera. This brings us to another crucial aspect: the distinctive shape of the tower itself, which is not merely aesthetic, but fundamental to its function. Natural draft cooling towers often feature this curved, swooping shape. Mathematicians call this shape a hyperboloid. Interestingly, it can be constructed using entirely straight lines, a fact that simplifies its building process significantly. However, straight lines alone aren't the sole driver of this design. A cylinder also uses straight lines. While the hyperboloid offers aerodynamic advantages, its wide base allows ample air intake, the constricted middle accelerates upward flow, and the wider top promotes mixing with ambient air. These are actually secondary benefits. The primary reason for this distinctive shape is structural. These towers are enormous. To achieve sufficient natural convection, a tall stack is essential. The taller the tower, the more warm, humid air it contains, generating greater buoyancy and increased airflow. The largest natural draft towers can exceed 200 meters in height and 120 meters in diameter. Furthermore, the walls are designed to be as thin as possible. Less material means lower cost and more area for airflow. However, a very tall cylinder with thin walls would be inherently weak, akin to a large, empty beverage can. The double curvature of a hyperboloid, however, stiffens the shell against both vertical loads, like the structure's own weight, and horizontal loads, such as wind. You can observe this principle yourself. A flat piece of thin paper offers minimal stiffness. Introduce a single curve, and it becomes significantly more resistant to bending perpendicular to that curve. The double curvature of a hyperboloid, often called the Pringle factor, provides even greater rigidity. My model demonstrates this well. Starting with thin, floppy acrylic strips, the assembled tower becomes remarkably strong. Using a hyperboloid can reduce structural stresses by half compared to a cylindrical tower, making such massive structures far more economical to build. This explains the distinctive shape of natural draft towers. But it certainly doesn't mean this is the only kind of cooling tower. Despite their iconic status, hyperboloid natural draft towers are relatively uncommon. This is because, while thermal power plants are large, specialized facilities, cooling towers are also widely used in HVAC systems for numerous large buildings like office complexes, hospitals, and schools. These towers often employ mechanical draft systems, using fans to create airflow instead of tall stacks. Even if they don't always possess the towering height, these systems are still broadly referred to as cooling towers. In fact, many power plants, refineries, and chemical plants also utilize mechanical draft cooling towers. Mechanical draft systems are less reliant on ambient conditions for airflow, are generally smaller, typically less expensive to construct, and provide greater flexibility when heat loads fluctuate. Furthermore, not all cooling towers use evaporative methods. Dry cooling towers incorporate internal heat exchangers, with the cooling water flowing in a closed loop. In dry systems, cooling is limited by the higher dry bulb temperature rather than the wet bulb, but there is no water loss due to evaporation and the buildup of minerals, common in wet systems as cooling water evaporates, is avoided. The prevalence of large natural draft towers at power plants is fundamentally linked to scale. The long-term operational savings, primarily from avoiding the energy consumption and maintenance of large fans, often outweigh the higher initial construction costs of natural draft towers. This is particularly true for nuclear plants, designed with operational lives of 50 years or more, allowing for cost amortization over extended periods. These facilities are also typically built in more remote locations, where land is cheaper and height restrictions are less stringent, making it feasible to construct such massive structures solely for cooling. They are especially common at nuclear plants for two key reasons. Firstly, reliability is paramount. Cooling is critical for nuclear plant safety, and systems with fewer moving parts, like fans, inherently reduce potential failure points during emergencies. Secondly, they suit the consistent output of baseload nuclear facilities, which typically operate nearly non-stop at a constant power. This allows for a system optimized for a single, steady heat load, unlike mechanical cooling systems that need to ramp up and down. However, even if the heat load remains constant at large baseload plants, the weather changes, and not every climate is ideal for natural draft towers. In dry climates, you might be familiar with evaporative coolers, sometimes called swamp boxes, which cool and humidify the air. It makes sense that these work better in dry climates, as less moisture in the ambient air allows for more evaporation and thus greater cooling potential. Therefore, one might assume natural draft towers perform best in areas with low relative humidity, but that's not necessarily the case. This concept took some effort to grasp. Let's revisit that psychrometric chart. Imagine an area with a wet bulb temperature of 20 degrees Celsius. Water from our condenser enters the tower at 40 degrees Celsius, and we aim to cool it down to 30 degrees Celsius. The air leaving the tower will be saturated at that target temperature. If the ambient relative humidity is, for instance, 20%, the air's path on the chart isn't a straight line. As it enters from the bottom, it first encounters the coldest water, moving towards the outlet temperature, before gradually veering towards the water inlet temperature as it ascends through the fill. Observing the lines for specific volume, a problem becomes apparent. In the initial segment of the curve, the air's state moves parallel to these lines, meaning it gains no buoyancy. Consequently, it won't rise effectively up the stack. While it might function at startup, as the water cools, the airflow within the tower would slow and stall, preventing adequate cooling. However, consider increasing the ambient relative humidity to 50%. The air's path on the chart still curves, initially towards the outlet temperature, before moving towards the inlet temperature as it passes through the fill. Crucially, its density consistently decreases along this entire path. This demonstrates why, for a given wet bulb temperature, cooling engineers find that a higher relative humidity actually creates a better draft. While seemingly counterintuitive, it highlights that natural draft cooling towers are less effective in hot climates. Even if dry air allows for significant evaporative cooling, the air may not become buoyant enough to naturally rise within the tower. For instance, both nuclear plants in Texas utilize large reservoirs for cooling. This illustrates the immense cost considerations in power plant feedwater cooling. In these cases, constructing and maintaining a dam and a vast lake proved more economical than building a cooling tower suitable for that climate. While that delves into some intricate details, it underscores the fascinating depth of engineering involved in such structures, and we've only just scratched the surface. The economics of constructing massive facilities like thermal power stations demand absolute certainty of design efficacy before any groundbreaking, leading to a vast array of cooling tower types and styles. Engineers meticulously select and combine designs and styles to achieve optimal efficiency for each specific application, resulting in an almost endless variety of towers to observe. And finally, a small admission. Some newer cooling towers integrate flue gas into their airstream, allowing the tower to perform a dual function. So, while I initially stated the plume isn't smoke, depending on the specific tower, there might indeed be some combustion byproducts mixed in. However, for the vast majority, that iconic plume is predominantly just water vapor. In a world often dominated by straight lines and right angles, it's truly satisfying when elegant, curvilinear shapes prove to be the most effective engineering solution for such a vital task.